Good morning, ladies and gentlemen. Distinguished guests. I'm Gautam Sivach, a representative from the esteemed Mechatronics Lab at the University of New Haven. Today, it is my pleasure to present our cutting edge research encapsulated in the paper titled Unveiling the Potential of Natural Language Processing in Collaborative Robots, Cobots, a Comprehensive Survey. Our focal point resides in the seamless integration of natural language processing into collaborative robots, embedded within the intricate framework of cyber-physical systems. This ambitious exploration seeks to transcend the boundaries of communication, decision making, and collaboration between human entities and cobots. The research approach, our research approach is designed to systematically categorize and analyze the landscape of existing NLP research. And in order to do so, there were different elements um, that we explored. Keyword analysis. We scrutinized the keywords associated with NLP research on cobots. This involved identifying and analyzing the terms and phrases that frequently appear in the titles, abstracts, and other metadata by relevance in research papers. And understanding the prevalent keywords, we can discern the thematic focus and key areas of interest within the NLP cobot domain. We also analyzed the published papers, the publication volume. We quantified and analyzed the volume of research output in the field, seeking to understand the trends. Our focus and scope is we're primarily focused on enhancing human-cobot interaction through the integration of natural language processing using CoboVox, a voice recognition system. And we also broadly integrate the NLP within the domain of cyber-physical systems with a specific emphasis on collaborative robots. So our two papers here listed emphasize a specific methodology that includes vocab building, language processing model analysis, and practical implementation of cobots with NLP to empower non-expert robot operators for efficient programming and controls of cobots using voice commands. Our papers involves categorization of existing NLP research on cobots, considering factors such as keywords, papers, and categories to comprehensively assess the significance and impact of NLP applications. At the core of our mission is the undertaking of a comprehensive survey. We aspire to thoroughly investigate the landscape of NLP applications and AI-assisted networking in the system, specifically as they relate to cobots. And by conducting this survey, we seek to uncover novel insights and emerging trends that define the current state of human-cobot collaboration. Our research will scrutinize three critical dimensions: real-time decision making. We are interested in understanding how NLP can facilitate swift and effective decision making process between human cobots. Collaborative interactions. Collaboration lies at the heart of human cobot relationships. We aim to explore how NLP can enhance the collaborative aspects of these interactions, fostering a seamless and intuitive exchange of information. And then the third one is training process. Training cobots efficiently is a crucial aspect of deployment. Foundations model, pre-trained and supervised data representations. Those are the utilization of pre-trained and self-supervised and adaptable data representation. These three foundational components serve as the bedrock for our exploration into natural language processing within the cobots. And pre-trained models, they're akin to seasoned experts in a field, have absorbed a wealth of knowledge from different databases. These models provide a starting point, a robust foundation that understanding the nuances of language and communication. You couple them with supervised learning and our systems becomes adaptable, refining its understanding over time without the need for extensive label data. And if you go onto the AI model evolution, transitioning into evolution of AI models, we observe dynamic progression across various categories of NLP on cobots. AI models when we talk about their evolution, we talk about advanced analytics. That marks the initial phase of our journey, characterized by statistical methods and predictive modeling. In this stage, data analysis primarily involves and revolves around traditional techniques, including regression, data mining. The focus is on delivering insights. And when it comes to machine learning, the evolution then ushered in the era of machine learning, where algorithm gains the ability to learn patterns and improve their performance over time, which then led to deep learning. As computational power surged and data availability expanded, we entered the epoch of deep learning, neural networks with multiple layers known as deep neural networks, and CNNs and RNNs. Now we have foundational models. Our journey reaches its contemporary phase with the advent of foundational models such as OpenAI, GPT-3, etc. Now let's elaborate on the different categories within NLP on cobots. Programming being one. Programming refers to development of systems that allow collaboration between cobots and humans to understand and execute commands given in natural language. This involves creating interfaces and algorithms that interpret human language. Application being the second one, category that focuses on real-world implementation of NLP on cobots. This involves deploying NLP capabilities in specific contexts or industries to enhance functionality of cobots. And then framework that forms the structural foundation for implementing NLP on cobots. It involves development and utilization of framework that facilitate integration of different technologies. And then comes security, which is a critical category in the context of NLP on cobots. As these collaborative robots become more integrated into various industries, ensuring security of NLP systems becomes paramount. So this includes safeguarding against potential vulnerabilities in natural language understanding processes and protecting sensitive data that may be involved in communication. And then lastly, implementation, that refers to practical realization of NLP capabilities within the operational framework of cobots. It involves hands-on deployment of NLP algorithms, interfaces, and systems onto collaborative robots. In summary, different categories collectively define the diverse aspect of NLP on cobots, ranging from the conceptualization of programming interfaces to the practical implementation of secure and application-specific frameworks. So each category plays a crucial role in advancing the capabilities of collaborative robots through natural language understanding. Now, our research journey extends into the networking, model construction, and development of specialized vocab tailored for discrete actions within collaborative robots. Networking being one, cobots like nodes in a collective, in a network, need to communicate efficiently. We investigate the networking aspects that enable seamless communication between cobots, ensuring a coordinated and synchronized workflow in collaborative environments. Then comes building models. The architecture of an AI model is akin to constructing a complex structure. Specialized task programming. Our research focuses on programming these tasks through spoken languages, providing a natural and intuitive interface for human operators to communicate instructions to cobots. In essence, our exploration spans beyond theoretical concepts to the practical intricacies of networking, model architecture, and task-specific programming. So this comprehensive understanding is essential for harnessing the full potential of NLP within collaborative robotics. Now let's elaborate on different mode of interaction with cobots. So chat prompt. In chat prompt, users interact with cobots through natural language conversations. This mode leverages NLP to enable users to communicate with cobots in a manner similar to chatting with a colleague. So the chat prompt mode is designed to be intuitive and user-friendly, so it allows more accessible and flexible interaction with cobots. And visual programming language that involves interacting with cobots through graphical representations and visual elements rather than traditional text-based coding. And then iterative interaction that emphasizes an incremental and feedback-driven approach. So users engage with cobots in an iterative manner where they provide input, observe the cobot's response, and refine their instructions based on the feedback received. This mode allows for continuous refinement and improvement of the interaction model over time. So it is well suited for scenarios where tasks may involve or require adjustments based on changing conditions, and fostering a dynamic and adaptable collaboration between human and cobots. And then fourth one is cognitive, that involves higher level of intelligence and adaptability in the cobot's response to user input. So this model leverages advanced technologies such as machine learning and AI to enable cobots to understand and interpret complex instructions. Voice system muting and microphone threshold. So the voice system employs a feature that automatically mutes the microphone if it does not detect any speech within predefined time frames, so known as microphone muting threshold. So this functionality serves the purpose of conserving resources and preventing unnecessary processing of ambient noise. So users have the flexibility to customize the microphone muting threshold, allowing them to adjust the duration before the voice system mutes the microphone. And what we try to do is to unmute the microphone and resume interaction with the cobot. User can trigger the system by saying different wake-up phrases like "Hello Marvin" or "Hello Glambert." Something we do say with iPhone, say Siri and Alexa for Amazon. And then clear communication guidelines emphasizes the user engagement with the cobots through voice commands. Speaking up and enunciating clearly enhance the accuracy of the voice recognition system, allowing for more effective interpretation of user interactions. Now we see the movement of cobots here. You have a free drive active. The free drive activation through NLP is important to understand because there might be payload on your cobot, and when you say free drive, that payload that is an end effector might be a laser machine that's worth a lot of value, and if you say free drive, it might just drop. So be careful when you're building a vocab. Make sure there's a prompt where it's asking you a question back, or guiding you in terms of if there is a payload or end effector in front of cobot. The four key areas of risks when we talk about security is around hallucination in the context of a human-robot cobot interaction, HCI. It refers to the potential for robot to perceive or interpret information incorrectly. And then bias is another significant concern, particularly in systems that involve AI and machine learning. Bias may manifest in the form of prejudiced decision making or actions by the robots based on the data it has been trained on. And then consent becomes a critical consideration as well. The risk here lies in instances where the robot or cobot may inadvertently violate privacy boundaries or engage in actions without explicit consent from the users. And then security risks pertain to vulnerabilities that could be exploited to compromise the integrity, confidentiality, or availability of the cobot systems. In summary, addressing these risks of hallucination, bias, consent, and security are essential for fostering safe, ethical, and effective human-cobot interaction. So that sums up our presentation here today. We can take questions, or you can write me. My email is gsiwa1@unh.newhaven.edu, and I'm also can be found on LinkedIn or Instagram or Twitter. And thank you today for listening to the presentation, and thank you for attending our session.